Ionization energy is the amount of energy that you need to fully remove an electron from the ground state of an isolated gaseous atom. And while most of the time we won't be dealing with isolated gaseous atoms, the trends in ionization energies are useful even under regular conditions. And this removal of an electron, this ionization, can be represented using an equation. So the equation shows an isolated sodium atom being ionized to form sodium ion and a single removed electron. And this represents the first ionization of sodium. The first ionization energy is the amount of energy it takes to remove that first electron from the neutral sodium atom. The second ionization energy for sodium is the amount of energy you need to remove the second electron. Not to remove two electrons, but to remove that second electron. And we can represent that with another equation. So this equation represents the second ionization for the sodium atom. And you can do third and fourth and fifth ionizations as you see fit. Something to note is the first ionization energy, the energy needed to remove that first electron, is always going to be smaller than the second ionization energy. And the second ionization energy will always be smaller than the third, which is smaller than the fourth, and so on and so forth. And it's possible to explain this trend of the first ionization energy being smallest and each subsequent ionization energy getting larger by looking at the electron configurations for the atoms and ions involved. So if we look at sodium going to sodium plus, we'll see the following electron configurations. The sodium to sodium ion conversion represents the loss of a single electron. And the sodium ion, with its fewer electrons, is going to experience fewer electron-electron repulsions. And now you can consider what happens when sodium ion loses an electron. Now you've got a situation where the sodium ion, with its fewer electron-electron repulsions, is going to lose an electron. It's going to be harder to pull that electron out of the 2p subshell because there are fewer repulsions that are blocking that nuclear charge. And these increases in ionization energy that happen as you remove more than one electron can become very, very large. Consider what happens when you're removing electrons from magnesium, for example. Removing a single electron is not that difficult. The electron is removed from the n=3 shell, which is fairly far away from the nucleus, and that distance from the nucleus means that it's fairly easy to overcome the attraction to the nucleus. Removing a second electron is a bit more difficult. There's now one fewer electrons contributing to the electron-electron repulsions, but it's still reasonably easy. So you're still removing an electron from the n=3 shell, which is still very far away from the nucleus, and even though there's a little bit more of that effective nuclear charge being felt by that outermost electron, it's still fairly easy to remove it. You do see a huge increase in the difficulty in removing an electron, so a huge increase in the ionization energy if you try to remove an electron from a smaller n-value shell. So consider what happens when you try to remove an electron from the magnesium 2+ ion. In this case, now you're not removing an electron from the n=3 shell. You're removing it from the n=2 shell, which is much closer to the nucleus, and it's therefore that much more difficult to overcome the effective nuclear charge. And we can summarize the trends in ionization energy by looking at left to right trends across a row and top to bottom trends down a group or down a column. So for example, we can look at sodium's first ionization energy versus magnesium's first ionization energy. Because they're in the same row, magnesium's going to have the same number of screening electrons as sodium. In the third row, all of the elements have 10 screening electrons. The difference is that magnesium has one additional proton compared to sodium, and that means its Z effective is going to be larger, which means that the valence electrons are going to be harder to pull away from the nucleus, meaning the ionization energy is going to increase. So within a single group, an up and down column on the periodic table, the trend follows the opposite trend to sizes. So as your atoms get bigger, the valence electrons are further and further away from the nucleus, and that means it's easier to pull them away, to remove them. Or, in other words, it's easier to ionize atoms as their valence electrons get further and further away from the nucleus. In potassium, the valence electron is in the n=4 shell, which is much further away from the nucleus than sodium's n=3 shell. And that means that the valence electron in potassium is much easier to ionize than the valence electron in sodium.